So far, this topic, we have been solving polynomial equations using various techniques. We've been trying to find zeros or solutions or roots, mainly by factoring is the most common or well-received method. But as the polynomials become more challenging to factor, maybe they even aren't factorable, or as the order becomes higher, it becomes more challenging to factor, and we need other techniques to find the solutions for a polynomial equation. Thankfully, we can combine a very traditional mathematical approach, which is unfortunately sometimes very labor-intensive, but we can use our calculators to make this process quicker and fairly painless if we do it correctly. So let's take a look here at this equation that we talked about in the introduction video that I talked about. This equation here, I mentioned that there's some hidden information within these equations. Some we've seen so far, some we will see in the next unit. But today we're going to focus in on the leading coefficient, this 4, and the constant term. These two numbers hold the keys to figuring out what the solutions or zeros or roots of the polynomial equation are. It gives us here this thing called a rational root theorem. Now, the rational root theorem allows us to list out all of the possible rational roots. Now, the word rational you may have seen before, but you might not know what it means. The word rational means it's a number that can be written as a fraction of two integers, basically. Numbers like 1/2, 3/4, 2/27, anything anything ugly, however ugly it is, if it can be written as a fraction, that is a rational number. If it can't be written as a fraction, something like maybe the square root of 17, that can't be written as a fraction, doesn't have any sort of pattern to it. That is an irrational number. So this theorem allows us to figure out the rational roots or the possible rational roots of a polynomial equation. It introduces these two letters, P and Q, and there's no real rhyme or reason as to why we use P or Q. P and Q are just easily distinguishable between each other, and you won't mistake them often for other letters. So P and Q. P are all the factors of the constant or the last term of my polynomial equation. That in this case would be the -3. Q are all the factors of the leading coefficient or the first term. That's this 4 right here. If we list out all of the possible factors of the end and the beginning, and then we divide them, that list of numbers will contain the rational roots of our polynomial equation. Let's take a look and see how this works. We can first start by identifying all of the p-values. Now, the p-values are the end, the constant term of the polynomial equation, and they include all negatives or positives. If we can somehow divide that number evenly by anything, it works. So positives and negatives, but we don't have to write like +1 and -1. We can just instead write plus or minus 1. The other factor of that -3 would be plus or minus 3. Those are the two factors of the -3 term. The first term is +4. That would be plus or minus 1, plus or minus 2, and plus or minus 4. Let's actually change this top color here to be able to look a little bit better. There we go. So now we have all of our P's and our Q's, and I wrote P twice. P's and Q's, plus or minus 1 and 3, and then plus or minus 1, 2, and 4. Those are the factors of the 3 and the 4. If we then write them in this P over Q format, we would have all of the possible X values. So we will have for, let's say we'll work with the 1 first. We'll have actually 3 different fractions. We will have this plus or minus 1 on top, and we can apply it to the plus or minus 1, plus or minus 2, and plus or minus 4 on the bottom. We can then move on to the 3, we'll have 3 different fractions. For the 3, the top can be plus or minus 1, undo that, plus or minus 3, plus or minus 3, plus or minus 3, and the bottom, those same things as before. Now, for this example, we actually didn't get any overlaps. If, for instance, we had maybe a plus or minus 2 also, maybe this last term was not just a -3, instead of maybe it was a -6. So we'd have a plus or minus 2 there on the end. When I divide these two fractions, this plus or minus 1, it gives me a number of 1. And if I did then the 2 over 2, it would give me a 1 again. There's no reason for us to repeat those duplicates. We can simply just, if we have it one time, we have it one time, and we're good. So if I take these here and I can simplify these fractions, this first one turns into just a plus or minus 1, a plus or minus 1/2, plus or minus 1/4, plus or minus 3, plus or minus 3/2, and plus or minus 3/4. That there is a list of all the possible rational roots for this polynomial right here. Let's actually take a look at the calculator and verify that. Here is the equation, the 4x to the 4th equation, graphed here for us. We see that it crosses 2 times. It looks like neither of them are whole numbers, so the -1, the plus or minus 1, the plus or minus 3 are out the window. But let's just see here by going, clicking kind of close to the 0, going menu, FCN, root. We see here that -0.5 is one of the solutions, and on this side, we'll go FCN root and say 1.5. So it looks like this option here, -0.5, and the other option of +3/2 are 2 of our rational roots. So we could expand the same idea here and tackle any polynomial actually by not starting with this list, because this list, the laborious way of doing it here would be to list out all of these values and then check them one by one using synthetic division. I can plug in a 1, I can plug in a -1, +1/2, -1/2, 1/4, -1/4, 3, -3. If any of those gives me 0 as a solution, or with synthetic division, 0 as a remainder, then that's a factor of the polynomial. That's the process. You start here and you just go through, guess and check. You have to do it multiple times. In this case, we have to do it 12 times. And we would come up with 2 of the solutions, but we wouldn't know when to stop, so we have to keep doing it 12 times. We can actually use the calculator to cut that out. If we start with the calculator, we start right here and say, okay, I know 2 of my rational roots, 0.5, -1/2, and 3/2. I can then go back, use synthetic division with those 2 values, and figure out the rest of the roots of my polynomial function. So that's what we're going to do in this section. Start with a calculator, and then figure out 2 or 1 or however many rational whole number, solid number roots there are. We can verify, and we should verify, that it does work with the rational root theorem, that the ones that we found actually are factors of P and Q, just to make sure we haven't typed something in incorrectly. But from then, we can use synthetic division to figure out the rest of them. Let's take a look at an example here. We have x cubed minus 5x squared minus 2x plus 10. So let's actually first graph this and see what we have going on here. I will take off this graph, put on this one. So here, hopefully I can zoom. Yep, great. Here is the graph of the function I'm working with here. There are, looks like 3 roots. I'm not sure if these first 2 are going to work for us. Let's see what they are. Menu, FCN, root. -1.41421. If I was asked to approximate or estimate what the root is, yes, this could be an answer. However, if I want to find an exact value, -1.414 is not good enough for us. I'm assuming this one over here is positive 1.414. So we want to figure out what those numbers are, but not using any sort of rounded or truncated decimal. I want the actual value of that irrational number. I think there is one here, though. It looks like one solid root is 5. So I know based on the graph that x equals 5 does work. And we can verify this by looking at The factors of 10 are like plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Oops, I'm going off the screen here. There we go. And the factors of 1 plus or minus 1. So we do have this 5 here, the 5 over 1. That does verify that we type things in correctly. It is one of the possible rational roots. We can just use 5 and jump directly to some synthetic division. So if I put my 5 out here with synthetic division, and then on the other side, I have a 1, I have a negative 5, a negative 2, and a 10. I should, if I'm still correct, get a remainder of, say it out loud, 0, yes. Let's just try it here and verify. So I bring the 1 down, I multiply by 5, I get a 0 because I'm adding these up. I get a 0 here, negative 2, multiply, add, 0. Yes. My remainder is 0, which is just further verification that 5 is a solution or a root of this polynomial expression. Now, since we are so good at synthetic division, now we know that these numbers, these coefficients here, turn into the expression x squared minus 2, and we can set that equal to 0. The great thing about this process is that when we do it, we should always be able to get down to a quadratic equation at the very end. Quadratic equations, we have lots of techniques to solve for. I could factor this. I could move things over and square root it. If I was really pressed, I could do the quadratic equation. This one's actually pretty easy. I could just add the 2 to both sides. I would get x squared equals 2. I could then take the square root of both sides and get my final answer as x equals plus or minus the square root of 2. We have to make sure we always add in that plus or minus there. We take the square root of both sides to capture both possibilities. And now we have our answers. X equals 5 plus or minus root 2. Those are all of our roots. I could verify there that the square root of 2 is 1.414. That's the same number that we saw here, that 1.41. That's the square root of 2, but I like the square root of 2 way more than I like 1.41. So like I said, if we get down to this point here, which we should always be able to get down to some sort of quadratic, we would then be able to do some technique, factoring this process or the quadratic equation to figure out our two irrational roots. And just as a quick reminder, the quadratic equation, x equals negative b plus or minus the square root b squared minus 4ac all over 2a. Not going to sing that one. So this last example here is a good example of a conjugate. So as we can see here, we have our values are plus or minus the square root of 2. And when we have irrational numbers, and also when we have complex numbers, we always have this conjugate pair. So a conjugate pair are two numbers that are basically the same, but one is a plus sign and one is a minus sign. We see this sometimes with, we've seen this before as like a plus b, a minus b, a difference of squares. Conjugate pairs always come in 2. So it's fine to have an irrational number like the square root of 2 or 2i, but if we have one, we have to have a partner. They always come in pairs. We've done some of these examples before with all positive integer solutions. This is a situation in which we have a complex number as one of our roots. In this case, we have 2i. But we can tackle this problem the same way that we would if we had just all rational integer solutions. What we do is we look at all of these, x equals 1, 3, and 2i, and we rewrite them in their factor form, their sort of binomial form. So x equals 1, that solution would come from the binomial x minus 1. If I plug 1 into that thing, I get 0. 3 would come from x minus 3. Now, the trick with either square roots or with complex numbers is that we typically only give you one of them, and then you have to know that you need the other one. So in this case, we have x minus 2i, that would give us the 2i, and then x plus 2i would give us the other one. So those always come in pairs, even though only one is listed. We have to do both of them. At this point, this is just a process of some more advanced foiling. I would FOIL those two together and those two together. If I FOIL the left-hand side, you would get x squared minus 4x plus 3. On the right-hand side, this is a great time to use that difference of squares shortcut. We know that a plus b times a minus b turns into a squared minus b squared. And so this over here would turn into x squared minus 4i squared. By squaring the first thing becomes x squared. Squaring the second thing becomes 4i squared. But we also know that I squared is equal to -1. So this becomes x squared minus 4x plus 3. The right-hand side is just x squared plus 4. You don't need this middle step. If you can recognize from here to here that you just square the first thing and then square this number with a plus sign, that is a nice shortcut. And now we can just FOIL this out. We would get x to the 4th plus 4x squared minus 4x cubed minus 16x plus 3x squared plus 12. Combining some like terms, we would get x to the 4th minus 4x cubed plus 7x squared minus 16x plus 12. This here would be our polynomial that has zeros at 1, 3, positive 2i, and negative 2i. So as a quick recap, we are going to be looking first to our calculators, defining what are the rational roots, verifying that that works with our equation, using synthetic division to get it down to a quadratic, and then solving for the irrational roots with either a quadratic formula, solving the equation, or sometimes even factoring. If you can factor it, though, then you've probably missed out on some of the whole number nice rational roots from before. In the next unit, we'll be taking a closer look here at the complex solutions to these polynomial equations. Thank you.